subject matter in Physics 212, both from an engineering perspective, maybe with the exception of geographical information system. But for pretty much every other field of study, thermodynamics is significantly more important and implications more profound than studies of diffraction, and for that matter, even optics. I didn't spend a huge amount of time on optics, but between the winter and my conference, clearly I lost a little bit of time, and I'm so used to catching up and using lab as a continuation of what we talked about here, and I can't do that, so I've not been able to make up any slack. So you do the homework for chapter 35, because some of you have. I wouldn't be surprised if TU's turned it in already. Consider it extra credit. I'll give you an extra homework assignment worth of it. Hopefully you talked a little bit about it with Greg. I'm not going to hold you to it because we've got 3 chapters to cover in 2 weeks for the final, and they're not easy chapters. It's kind of the equivalent of maybe chapters 5, 6, and 7 early on. Newton's second law, or I'm sorry, Newton's laws, work, energy and momentum, maybe even chapter 8, all sort of wrapped up in 3 chapters. So we got a lot of stuff to do. To the extent that you've had some chemistry, some of you maybe, some of you not, that some of it may feel a little bit more familiar. A lot of what we'll talk about will hearken back to the beginning discussions at the start of the quarter when we were talking about fluids, and just some of the subtle relationships that are involved internally. Good morning. So I have your exams about 80% graded.
Hey, that's nice.
Well, I give you a week to do your stuff. Give me a week to do mine. I in a perfect world, I would have had it all graded Friday, but I had 8 hours of committee meeting on Friday, and so it was. Last week's a very long week, so I've gotten my other class. They took their midterm before you guys did. Their stuff is done. Your stuff is close, but not quite done. I will say, at the moment of the 14 out of 17 grade, 13 out of 17 graded. The average score right now is about 72. The high is about a 90%. Low is not. There aren't any like super lows. I think the lows are somewhere 60% so far. So not as good as I'd like, and I don't know if I'm grading the higher or the lower section as I finish up. In the so I suspect that would be fairly consistent with what the average is overall. And if I were going to make a simple observation from everything I've seen right now, surprisingly, significant, maybe not a majority, class couldn't do a ray diagram. And you lose like 2 points on ray diagrams right off the bat. Not everybody, but just 3 points actually. So right there, there's what, 30%, not 30%, 15%, 8%, something like that of the grade. So, yeah, I don't know. I thought that was a little bit odd. In any case, no, yeah, but it's early in the morning for me, so been up a while, but it still feels early. So just, if you think about how you did in your ray diagrams, that's probably a good indication of where you were on your exam, generally. So, what it is. Okay, so we have 3 chapters that I don't even necessarily think can be considered discrete or independent entities. It's basically one fundamental idea, but just ultimately some layers deep in that idea. So as we approach the next 2 weeks, and your last 2 labs will be relevant to this as well, essentially everything encompassed together comes down to this. The idea and the significance of temperature and its relationship to energy, heat. Now you say, well, heat, isn't that a form of energy? Well, technically, heat is energy transfer. And ultimately, work. And encompassed together, this topic, at least at this level, comprises what we call thermodynamics. So up to this point, we basically ignored temperature effects. We've looked at non-thermodynamic systems because we haven't dealt with any aspect of heat transfer other than friction, which as a drag property or a non-conservative interaction results in usually heat generation as friction is developed, for instance, kinetic friction, even air drag is another example. But we didn't deal with it or delve into it any further than that. So, but this is everything that's left. And all of the ideas are relevant and consistent with interactions in solids as well as fluids. But we will use as a fundamental, when we get deep enough that we're looking at very specific interactions or situations, we'll deal primarily with gases. And the reason is it's much easier to describe the basic behavior of gas systems compared to liquids and solids because of the increased number of interactions that are involved. You don't just have things bouncing into each other, but you have chemical interrelationships and all kinds of things that we don't want to have to deal with enough time. And pretty dicey stuff. The whole chapter's on fluid thermodynamics and fluid mechanics and what have you. So I'll start by, let's see, I think I've got these things up if the network's working. Using some overheads to get us going a little bit on this so I can talk more and write less. Yeah, like I need to talk more. Also, as we go to the end of the term, for those of you that are A, interested, or B, maybe struggling and need more time and basically FaceTime with me, Tuesday and Thursday afternoons, maybe the exception of today, barring anything that comes up, committee meetings or something that department meetings that I get dragged into, I'm going to try to be around in the afternoons on Tuesday, Thursday. Now you have class. I don't know what your class schedules are, but on Tuesday, Thursday, I know you're here. It makes you really want to do more physics during the day. But maybe, 12 o'clock's my office hour, but 1 o'clock until maybe, 2 or 3, I'll be around. And I think this room is even open, so we can talk more, discuss more. And when we get to this stuff, there's some finesse that you have to definitely get comfortable with. Also, I'll be around on Fridays, again, 3-hour lab. I can't be here I can't be available for you guys Monday, Wednesday, but also Friday afternoons. Try to be available. So take advantage of that time, especially if it's communication issues, things you want to discuss, because you can't, kind of like a Ray diagram, you can't fake it. And this can really kick your ass if you're not comfortable with it, so to speak. And practice, perspective, best you can do. Okay. So please, I want to be your resource. So please, if you can, make an attempt to spend some time on those days in the afternoons. Okay. All right. So let's just sort of lay out some basic ideas, and I don't want to be redundant to the extent that maybe some of this stuff is obvious or super familiar to you, but let's just lay out the basics, some of which is a repeat of our very first lecture at the beginning of 212. To beginning, when we refer to the idea of temperature in an observational sense, we really sort of think of it in terms of how hot or how cold something is. But really, first of all, that's kind of a misnomer in general. When we talk about things being hot or cold, for instance, when we touch things, we aren't really gauging temperature. We're gauging temperature differences. The colder our hand is, the warmer our surroundings appear to be. So you go outside, you dig around in the ice. TU plays with Oscar for an afternoon in the snow. Come inside, your hands are freezing. You stick your hands under cold water. They can feel scalding hot. So what we typically think of as a hot or cold in a temperature sense, when we physically sense things, we don't really experience temperature. We experience temperature differences. Is heat flowing, energy flowing in or flowing out? Now, to that end, temperature itself is not an energy. It's a base fundamental quantity in an SI unit sense, in a physical sense, but it is not energy. Now, we've developed a temperature scale that allows us to scale it or relate it proportionally to energy, but it's no more an energy than electricity is force. Even though we measure with force sensors voltages and say, oh, that corresponds to a certain weight or to a certain force, Newton value, right? We've done that. We do all kinds of calibration. pH meters do not measure pH. They measure voltages, and we relate them to pH. Okay, so just keep in mind, temperature, not an energy, but it's very indicative of the presence of or state of energy in the system. Now, more specifically, the idea of temperature, as we describe it or think about it, it's related to the internal motion of a given system. And usually, we refer to the random internal energy associated with something that we call the closed system. So we're not worrying about, you take a balloon, and that balloon is moving along, it has a certain velocity and a certain kinetic energy based on its mass and how fast it's moving relative to how fast we're going when we observe it. But within the balloon, you got all the little gas particles bouncing around. All of that stuff inside is internal. We call it internal energy. And that's separate from the mechanical energy of the system on the whole as we look from the outside. So usually we can't really see what's going on inside, but we can make some inferences and observations about it. So to this end then, right, the faster the vibration or random bouncing around motion inside any given system, the more temperature we say it has, or the higher the temperature is. And the less motion, the lower the temperature. Now we'll get to how they did it, but if you extrapolate this all the way back, when you have zero motion, or when you approach zero random or internal motion, based on this criteria, your temperature approaches zero. So the temperature scale that we want to use is the temperature scale that corresponds to relative increase in internal motion, and how that corresponds to temperature. And also, when you extrapolate that all the way back to zero motion, zero temperature. Okay, that's the thermodynamic scale we're going to use. That's the Kelvin scale. Now to this end, we have three temperature scales that we've probably all dealt with at one point or another. Fahrenheit scale and the Celsius scale are both based on water. It's the most common fluid around us, the easiest thing to deal with, and most ubiquitous substance from a biological relevance. Anyway. And to this end, the Fahrenheit scale was established really to measure weather. It's basically a weather scale based on temperature or based on critical properties of water. Celsius scale was established to be a more scientific scale, but it's still based on the properties of water. And again, kind of like a grade in a classroom, High score, you approach 100. Low, you approach 0. Well, in the sense of liquid water at atmospheric conditions, liquid water doesn't, under normal circumstances, it can't go below 0 Celsius, or it can't go below its freezing point, if you will. So that's a good place to stop a temperature scale if we're going to use water. So let's just call the point where water freezes, no longer liquid, that's 0. Cold, cold, cold water, as cold as it can get. Warm up water, again, atmospheric, can't get above 100 unless you use extraordinary conditions like a pressure cooker. So hot, 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 liquid water, let's call it 100. Now we've got a scale for the properties of water based on the absolute existence of water in a liquid form. And for doing water-based chemistry in the 1890s, early 1900s, kind of a nice temperature scale. It's probably the best scale you could use for cooking. The closer you get to 100, the more likely something is done, because most everything we eat is filled with water. And we want to refrigerate it to keep it preserved without freezing it. The closer you get to 0. So we usually or rarely use it, in this country anyway, as a cooking scale. But Celsius is an ideal cooking temperature scale. The scale we're going to deal with, and as a general rule, keep this in mind. Any calculation you use temperature, and I've said this before, even if you don't necessarily have to, you're better off 99% of the time using Kelvin in any temperature calculation you make. Okay? So the Fahrenheit scale is really a weather scale. Celsius is basically a liquid water scale. For whatever purpose you may be cooking, you would use water in its fluid, liquid state. And the Kelvin scale is what we refer to as the thermodynamic, or if you will, this pen's about on its last legs, physical temperature scale. Now, the way we've established it, there's a very intimate relationship between Kelvin and Celsius. But ultimately, as a general rule, you use Kelvin. You cannot go wrong if you use Kelvin temperatures. There are times when you can use Celsius in lieu of Kelvin without losing information, but almost always, if it involves temperature in the calculation, pick Kelvin. Okay. In the same way we usually think of meters, except sometimes in optics. When you're using length, measuring using time, use seconds, temperature, better safe than sorry, use Kelvin. Now, lastly, before we move on, I'm going to set it up here. Here's an important and interesting point. The internal energy of any system, average internal energy. Now, when I say internal energy, what energy might be the first thing that should come to mind when we talk internal? Another name for internal is thermal energy. But when I refer to that concept, the first thing that should come to mind is what might that be? Kinetic energy. Because it is fundamentally a kinetic energy. It's just a random, uncontrolled kinetic energy inside. Whether it's a vibrational or whether it's just bouncing around, it's kinetic energy. So average, in other words, the energy of an individual particle inside a system is directly proportional to temperature, or vice versa. If you know what the temperature is in Kelvin, you can immediately ascertain approximately how much energy a particle has in that system. And I might even extend this a little bit further. Without making it a specific concept, we might even extend this and say that the average internal energy is proportional proportional to not just the temperature in Kelvin, but the Boltzmann constant times temperature in Kelvin. Especially gases. When we refer to the energy of motion in a system, it's almost always highly, highly tied to the product of kT. And when you get into engineering thermodynamics later, you'll see kT all over the place. And we've already seen it once. Remember where we've seen it that the one time?
Speed of sound.
Speed of sound. Because we're talking vibration of little particles, movement in the air. And internally how waves of energy pass through that random motion. So we've already seen it in a very tangible way. And again, one of the things that you'll constantly want to keep in mind is the value of the Boltzmann constant. And you don't have to remember many constants, but definitely keep track of the Boltzmann constant.
Negative 23.
Negative 2,3, if I can draw it, write it clear. If you want to know kind of where that comes from, it comes from Boltzmann's idea of looking at the physics associated with closed thermal systems and identifying that, well, if you've got a gas, think of it as little particles of mass bouncing around, and each particle has, on average, some energy related to K times T. Well, his understanding, his approach to this predates the complete establishment of the atomic hypothesis of matter. Okay, so people still argue, people with names like Mach, Poisson, argued with Boltzmann and sort of dismissed his ideas because it wasn't clear at that point that matter consisted of these discrete little particles. So highly significant. Okay, so that's really temperature. Now, in case it's not obvious, I will just sort of, some stuff that I'm always wanting to jump over as soon as possible. So, the distinction between the Kelvin and the Celsius scale is strictly what you call the y-intercept, or the 0 point. So, the freezing point in the Celsius scale for water was established arbitrarily as 0. Boiling point, atmospheric pressure, 100 Celsius. But what a very clever group of scientists did, and I love this experiment, was to take information on the energy of a gas system in Celsius units, plot it on a Cartesian graph while you still have a gas, and then take that line and extrapolate it back to the x-intercept. So think about this as measuring the pressure of a gas. Gases are really easy to measure because temperature and pressure are directly proportional when you're at constant volume. And measuring it as a function of temperature in Celsius and getting a series of data points. So temperature goes up, pressure goes up. It's kind of an arbitrary thing because it's on the Celsius scale. You get enough points. Now at some point all gases typically condense into a liquid phase, so you only have a limited range of data depending on the gas you use. But if you get enough points that you can do a best fit linear regression, you can estimate the temperature in Celsius at which the pressure is 0. In other words, the 0 pressure temperature. Well, what is it that is responsible for pressure when you're measuring it in a system? It's molecules bouncing around on the sidewalls of the sensor, right? No motion, no collisions, no pressure. So the extrapolated thermodynamic temperature, or Celsius temperature, where the pressure is predicted to be zero based on a temperature, pressure, gas series of experiments, leads to negative 273 Celsius, 273.1. So there, we then established a thermodynamic temperature scale. No motion, no pressure. Let's call that zero temperature.
And they did this with every gas, I guess, or?
That's the beauty of it. You use more gas in the same container, you'll get a more extreme pressure-temperature relationship. But the beauty of it is they did this experiment with helium, carbon dioxide, oxygen, all these other gases, and we'd always get these graphs that might look different, but they all had one thing in common. When you extrapolate it back, you always got the same number, even though the slopes themselves weren't the same. They always predicted a singular temperature value in Celsius. Now, the reason all the data is over here, and I don't know, I'm using water as a fundamental example, or the 0 Celsius. Helium might get you down here, neon maybe somewhere in here. Carbon dioxide, you might get to there before it starts to sublimate or deposit, going to solid form. But when you stay in the gas state and measure the relationship between pressure and temperature, hearkening to, if you will, the ideal gas law, it always experiments pretty closely, right, within experimental area. It collapses on negative 273 Celsius. So we call that negative 273 then the zero pressure temperature, 0 Kelvin, or absolute zero. Can't get below that because you can't have negative motion. You can't have negative motion, or you can't have zero pressure. You can't have negative pressure. You can have pressure differences, but you can't have a negative pressure. So there's no, physically, there's no, what's the word for it? There's no condition, certainly in the 1800s, where you could have a temperature below this 0 point. In fact, it's really hard to get to it.
Is there an opposite where you have a maximum energy density, like for the molecule at the speed of light or something like that?
No. And the reason is, when you reach a certain temperature at a high level, and it depends on the atom or the substance. If temperatures get hot enough, the collisions literally knock electrons off the molecules or the atoms. And then you have the plasma state. But there's no reason that the plasma state can't get hotter and hotter and hotter if it were possible. So it's open-ended on one end. We've just fixed the 0. Now, hypothetically, I don't think anything has ever been seen beyond a few million Kelvin. But there's no intrinsic reason why you couldn't get hotter. At least not that I'm aware of. So, we may do an example of this in this week's lab. It's a very cool example. I think it's ingenious that you can estimate where the pressure should collapse to 0, even if you're not even near where that should happen, just by looking at a pressure-temperature relationship for an isolated gas. Beautiful, beautiful idea, and it was ingenious that they had come up with it, or even thought about it. Okay, so nonetheless then, what that does is that it fixes this Kelvin scale at an absolute 0 corresponding to no pressure in a system of gas if it were at that temperature because there's no motion. That absolute 0 on the Kelvin scale corresponds to negative 273 as it's accepted today, 0.15 degrees degrees Celsius. Kelvin, base unit, we don't talk about it in terms of degrees. Degrees are a term for identifying it as a relative quantity on an arbitrary scale. Now, the other thing, though, is that if you look at the incremental size of a single Kelvin unit, it's the same as a Celsius unit. So, temperature in Kelvin corresponds to temperature in Celsius, but we have to add the fact that when you're at 0 Celsius, you're already 273 temperature units above the absolute point of 0. This is the simple equation, but what's implicit here, and most people never pick up on this because we just like equations. And anytime you're talking physical, to go from one unit system to another requires that you have a unit conversion. In the unit conversion, the relationship between the numbers, 1 unit Kelvin corresponds to 1 unit Celsius. So there's implicit in this calculation that you've probably seen before, is that you're multiplying, when you take a Celsius unit and you convert it into Kelvin, you're implicitly converting the temperature in Celsius to equivalent Kelvin units. Celsius units then cancel out, and then you add the 273 to get the y-intercept where it ought to be. So to this end then, these are incremental unit changes in temperature. So 1 degree Celsius change in T corresponds to a 1 Kelvin change. The Kelvin scale. Or anytime you look at a temperature change, like you take a glass of water and it starts out at 5 Celsius, and then it warms up to room temperature, say 25 Celsius, there's an increase of 20 degrees Celsius in the temperature of the water. Well, regardless of the absolute numbers, the change in temperature on the Kelvin scale is still 20, is also 25 units. So the changes are always equal. And I'm not sure if it's easy to recognize this, but a Celsius or a Kelvin scale is just a Celsius plus 273. So if you take 2 Celsius numbers and subtract them, the 273s are subtracted against each other, and they go away. Got a temperature plus 273 minus a temperature plus 273, and the 273s cancel out. So incrementally, it's the same. So sometimes it's easier to use Celsius, but again, when in doubt, always go Kelvin. You never go wrong there. Okay, so then, two things that we can say now. Here's where it gets maybe interesting. I want to put the next thing up here. I might be jumping the gun, so I forget what the next overhead is, but let's sort of establish something. When a system absorbs or gains energy, different things can happen. What happens to a system, or what can happen to a system when it gains energy? And I'm going to make this okay, so I don't mean take a baseball and throw it, and then you've accelerated. But internally, when a system gains thermal energy, I can't even say internal energy because there are situations where you can gain energy and it doesn't become internal energy. But we'll deal with that another time. But when a system gains, bad enough, I leave letters out, much less have it on video. When a system gains thermal energy, you've got multiple possibilities. again, this is where just filling in the gaps of understanding, I think, is important. But what can happen when something gains energy? Well, one possibility is the temperature will change. Regardless of Celsius or Kelvin. Something gains energy, it's temperature change.